there, and hey, thanks for clicking on the lesson for class. This is a lesson that begins our second unit of study. In this unit of study, we're going to be talking about real numbers and exponents. And we're going to start off the unit by talking about a lesson that talks about rational numbers. If you have your textbook handy, that's lesson 3-2, can be found on page 128. Definitely a lesson and definitely a whole unit really that's going to require you to use a calculator a lot. That's probably going to be a common thread all year long, so it's always a good idea to have a calculator handy, paper and pencil, and a textbook there as needed just for reference. So we're going to go ahead and cover this lesson now. Thanks for watching it ahead of time, and then when you come to class, we're going to be doing problems that come directly from these notes today. So hopefully it all sounds familiar and looks familiar. So the definition you see on this page says that rational numbers are any number that can be written as a fraction. Now, this might sound familiar to some of you, and it might sound like something you've never heard before, but any number that can be written as a fraction is called a rational number, and that would even include things like decimals, right? Like this decimal here is 0.87. I'm going to show you in a few minutes how you can actually turn that into a fraction. Negative 23, that can very easily be written as a fraction. Next up here is the mixed number of 2 1/3. Currently it is in mixed number form. I'm going to show you how to turn that into a fraction. It's going to be an improper fraction. I can tell you that. Do you remember what an improper fraction is? Well, you're going to remember pretty soon. We're going to do some examples. A number like negative 2.56 is rational. I'm going to show you how to convert that into its fraction form. And even a positive whole number like 1 can very easily be written as a fraction. And I'm going to show you how to do all of these here in just a minute. So what you see next on this page is this diagram, this design. The way this design works is you have to look at it as the pink circle in the middle. Think of that as a balloon, right? And it's containing some numbers. And then it is inside a bigger balloon, right? That would be that greenish blue balloon called the integer balloon. And then that bigger balloon is inside a box, and it's inside a box called the rational numbers box. So if we start on the innermost balloon, that's that pink circle called whole numbers. Any number from 0 on up, anything that's in the positive end of our number system that doesn't involve any decimals or fractions. So again, there's some examples there, 0, 1, 2, 3, 25, 38, 100. Those are all whole numbers. The whole number bubble only contains numbers like that, right? There's no negatives, there's no decimals, there's no fractions. But that balloon is inside the integer balloon. So now I'm looking out here kind of in this teal or turquoise area, this greenish blue area. Integers, when we start talking about numbers that can be called integers, we start bringing in the negatives. So we have like the -1 and the -12 and the -70, so on and so forth. We still are not introducing any decimals or any fractions, so they aren't being classified yet, but at this point we've covered whole numbers, and now we're talking about numbers that can be called integers. So what's interesting to note is that integers are not just negative numbers. Integers are negative numbers, but they are also all of the whole numbers, right? Because a whole number balloon is inside the integer balloon. So all of the whole numbers are also integers, but the integers do bring in these outside numbers, these negatives. Now notice that the negatives, like this -12, it is not in the integer or the whole number balloon. So a negative number like -12 cannot be called a whole number, right? He's not in that part of the design. Okay? Now, outside of the integer balloon, just floating around out here inside the purple box, these are our rational numbers. So here is when we're going to introduce things like decimals and fractions and mixed numbers and repeating decimals and negative fractions and negative decimals and all of these numbers that are, sometimes they can be a challenge to work with when we see numbers like this in our math problems. So out here in the rational numbers, we have like 0.5. That's a rational number. I could write that as a fraction. -1/2, right? That is a fraction. 2.56, or 2 and 56 hundredths, which is a repeating, right? Remember that little bar over the top means repeating. So that would actually look more like this, so on and so forth if I were to keep writing it. Negative 1.7, that's definitely a rational number. And even down here in the bottom left corner, negative 10 and 2/5, that is a rational number. So you have to try to think of this design as such. Imagine that it's like a one-way street. I guess you can kind of think of it that way. Numbers that are in the inside, in here, in the whole number bubble, or the whole number balloon. Let's look specifically at 1. 1 is in the whole number balloon. It is also inside the integer balloon, and it is also inside the rational numbers box. So 1 is actually all of those things. 1 can be classified as a whole number, and an integer, and a rational number, because it's inside the box, and it's inside both balloons, or both bubbles. What about negative 12? What could it be classified as? Is it in the box? Yes, it is in the box, so it is a rational number. Is it in any of the balloons or the bubbles? Yep, it's in the integer bubble. Is it a whole number? No, because it's not in the whole number. So 12 would be called an integer, and it would also be classified as a rational number, but it is not a whole number, right, because it's a negative. And then if we work our way out further yet, like negative half, it is only inside the box, so it is just a rational number. It is not in the integer, no. It is not in the whole number balloon, no. So a number like negative 1/2 can only be called a rational number. So when I say it's like a one-way street, it's like numbers cannot work their way into the balloons or the bubbles. But a number that's already inside, like 1, does work his way out, right? 1 is a whole number, and he's an integer, and he's in the box, so he's a rational number. So that might be one way that helps you kind of realize how this classification system works. It can be a little bit tricky, but hopefully if you look at this design, hopefully that helps you kind of learn how to separate the different categories of numbers. So there are some really oddball numbers that do exist in our number system. They're called irrational numbers. Well, irrational numbers are not in that design that you see on this screen. They're not on there. Well, that's because they would be floating out in space. You have to imagine that irrational numbers are like our crazy wackadoo numbers, and irrational numbers would be floating somewhere out here. They are not even in the box at all. Now, what's an irrational number? Well, that is a number that cannot be written as a fraction. And that is because it is a never-ending, never repeating decimal. So probably the most popular, most famous irrational number is pi. I know that you guys know what pi is. We usually substitute in a 3.14. However, that's really just an estimate of pi. Pi is really a decimal that never ends, and it does not have a repeating pattern. And because of that, you are unable to write it as a fraction. And if you cannot write it as a fraction, it is not a rational number. So I have some examples here, right? There's that beginning of pi, 3.14592, and it just continues and it never ends. Here's another irrational number. It does not really have a repeating pattern because it's 8.7877877778. If it were just 8.7878787878, then I could write it as a fraction. But the way that number is written now, it never ends and it never repeats, and I could not write that as a fraction. And I'm going to show you, like I said, I'm going to show you how to do all of this. In fact, I'm going to show you right now. Get your calculators out, fire them up. Here we go. Write each number as a fraction in simplest form. Whole numbers are easy, and integers are easy. So this is an integer, negative 23. If I want to write that as a fraction, all you have to do is put it over 1. Right? That's pretty easy. How about right below it here, the number 7? That's a whole number. 7 over 1. Right? Pretty easy. How about over here in the right, the top right, this 6 and 1/6? That's a mixed number. I want it as as just a fraction. You remember how to do this? You take the big 6 times the denominator and then add the numerator. So 6 times 6 is 36, add 1 is 37. Remember doing that? That becomes your new numerator. And the denominator stays the same. So even though it's an improper fraction, right, the top number is larger than the bottom number, the numerator is larger than the denominator, it is in fact in fraction form, and therefore it is a rational number. Below that we have 4 2/3. So it's 4 times the denominator of 3, that's going to give you 12. Add the numerator of 2, that bumps us up to 14. That's my new numerator. And the denominator stays the 3. Again, an improper fraction, but a fraction nonetheless, thereby classifying it as a rational number. A couple more to look at here, going down to the bottom left corner with the 0.64. It's decimal. The trick to writing decimals as fraction is all about place value. Look at the digit in the far right position. It's a 4. See it over there? Remember what place value that is? Hundredths. That's important because that's what becomes your denominator. And what becomes your numerator? The 64. And then of course this is 8th grade math, and they're going to ask you to write these in simplest form, which would mean you have to simplify them down. And if you reduce this down, it does go down to 16 over 25. Lots of calculators have a function that will simplify a fraction for you with the push of a button. Otherwise, you can always divide it down. Divide by 2, divide by 2, divide by 5, divide by 5, and keep going until you get it down to simplest form. The next one, 5.875. Well, I see a whole number of 5 here. Leave that guy as a whole number. Now, let's look at the decimal portion, this 0.875. Let's look at this. What place value is that 5 in? Do you remember? I have to think back to the days when you were learning your place value chart. That's the thousandths place. So I'm going to say that this is 5 and 875 over 1,000, which simplifies down to 5 7/8. Technically, that's not fraction form. Technically, that's still a mixed number. And really what you should do with that is put it into fraction form. So now you would take your 5 times 8, which would give you 40. Add the 7. Now you have 47 as your numerator and 8 as your denominator. Now it's a fraction, and that's ideally what they want you to do. So even with those really huge numbers like 875 over 1,000. Simplify it down, keep simplifying it. We got it down to 7/8. Then take that mixed number and turn it into an improper fraction. Just as a side note, it looks like this is going to be another 2-video lesson when it's uploaded to YouTube. So just keep that in mind, okay? We're almost done, just a few more. Sometimes we are faced with repeating decimals, and they can be a bit of a pain, not gonna lie. Let's look at this example that I have here. 0.6 repeating. What does that really mean? It really means this. Forever and ever and ever, never ending sixes, right? Well, the simplified way of writing that is shown with a little line over the 6. I know you guys have seen that many, many times. So there it is. And if we want to write this as a fraction, the trick is to subtract 1 away from the denominator that you would ordinarily choose if it wasn't a repeating decimal. So if this was just 0.6, and we were going to write that as a fraction, I would ask you, what place value is the 6 in? You would tell me it's in the tenths place. So you would tell me 6 over 10 if it wasn't a repeating decimal. But it is a repeating decimal. And when it's a repeating decimal, you have to take 1 off of the denominator that you would have otherwise chosen. So now instead of choosing a 10, we take 1 off and it becomes a 9. So that's where that 6 over 9 comes from. And yes, it would simplify down, really, to 2/3. Ideally, that's what you would write as your answer. So let's try a few of these. Okay, 0.42 repeating. What place value is the 2? It's in the hundredths. But because it's repeating, we're not going to use 100, we're going to use 99. 42 over 99 simplifies down, if you divide both by 3, to 14 over 33. And guess what? If you were to actually take your calculator right now and punch in 14 divided by 33, you would get an answer of 0.424242424242, and it would never end. Okay, let's look at the next one. 0.36 repeating. It's in the hundredths place, but we can't use the hundredths because it's a repeating decimal, so we're going to use the 99. 36 over 99, and simplify it down, 12 over 33. Simplest form. And again, if you were to take 12 divided by 33, you would see that it equals 0.36363636, and it never ends. The last thing we're going to talk about in this lesson and in class is we're going to practice identifying all sets to which numbers belong. In other words, how many ways can I classify these different numbers? So think about the number 0. Think about that chart that you saw in the very first slide. Where was 0? It was on the innermost bubble, right? So it was in the whole number bubble, or balloon, which is also inside the integer balloon, and both those balloons are inside the rational number box. So if I were going to classify 0, I would say that it is a whole number, it's also an integer, and it's also a rational number. What about a number like 1 4/5? Well, it's not a whole number, and it's not an integer. Think back to that design, right? It's just a rational number. Fractions and decimals were floating out there in that purple box. They were not inside either one of those bubbles. What about this thing? 1.41421356 going on and on and on. It never seems to end, and I don't see any kind of a repeating pattern there. What do we call numbers that don't end and don't repeat? Irrational. It's an irrational number. I could never, ever, ever write that as a fraction. Well, that pretty much covers it. We've talked about how to identify and classify rational numbers and irrational numbers. I've showed you how to write them all as fractions, including whole numbers, including integers, including mixed numbers, including decimals. And now when we get to class, this is what we're going to be working on together. And hopefully now you have some notes that you can use for reference. And of course we're going to be working in groups and you guys can help each other out. And I'll be walking around to make sure that you're on the right track. Thanks for watching. Bye-bye.